guys, Don Dimugot here, MSU-1 student. Today I'm going to perform laboratory activity number 1, the tool familiarization for Altera DE2-115 and using the computer-aided design software Quartus. Join me as we explore the FPGA board and the Quartus. Okay, so we are going to use the QuartusPrime 20.1 Lite Edition as our simulator for our Verilog HDL codes where all the necessary components, features, interface, and mechanics are coded and compiled using these tools. So to start, let's open the Quartus icon, okay? Then once you open it, select new project. Again, select new project. Then click next. Okay, so after that one, a new project wizard window will appear. Then you create a folder entitled your desired name for your folder. So since I already created a folder, I will use that folder, okay? One here, then this one here is you type the name of your project. So let's say counter. And then after you type it, then click this next icon here. Okay, for project type, you just select empty project, then next. Okay, so just click next once you see this window. Okay, just click next, and then here you need to choose specific device selected in available device list. Okay, since we are using Altera DE2-115 Cyclone 4E, so we need to find the EP4CE115 F29C7N, or I repeat, EP4CE115 F29C7. Okay, EP4CE115 29C7. Then just click next. So here just click next. Okay, so a summary window will appear such as this one. Okay, the details, it shows the details of your project. Then click finish. Okay, so just wait, and then to create a Verilog file, you just click the new icon here, this one here, new icon, and then select Verilog HDL file, Verilog, this one here, Verilog HDL file, then click OK. Okay, then this one here. So in this portion, the Quartus graphical user interface, it includes a project navigator. So this one here is your project navigator, this one here. project navigator, which consists of the design hierarchy, files, and design unit. It also has a task window to start compiler module individually. So the task window also allow you to change settings or view the report file for the module, or to start other tools related to each in a flow. While the design entry, this one here is your design entry, is the working directory for your Verilog code. So this is the task window here. This one here is the tasks window. This one here is again the project navigator and design entry. Okay, so that's it for the Quartus basic. So this is the layout of the Altera DE2-115 board. It indicates the location of the connectors and key components. So let's try to verify this one to the actual board, which is this one, guys. Okay, this is the actual board. Okay, so let's start with this one. So this one is the USB blaster port. Second one is the USB device, USB host. This is the mic in. Okay, mic in, line out, and this one here is the video out. Okay, this one here is the video out. This one, video out. Okay, and this one is the VGA out. Okay, this is the Ethernet 10 100 to 100M port 0. Okay, this is the another Ethernet port 1. Okay, and this one here is the RS232 port. Okay, this one here. Okay, so this one here, notice this one is the 12 volts DC power supply connector, and this is the power on and off switch. Okay, so let's try this one. Okay, there you go. Okay, so let's just off it. Okay, and let's proceed. So next is the Altera USB blaster controller chipset. This one here, this one, this two. This is the Altera USB blaster controller chipset, and the USB host or slave controller is this one here. This one, guys. Okay, so another one is the Altera EPC S64 configuration device is this one here. This one here. This one. That is again Altera EPC S64 configuration device. Okay, so let's move on with this one. It's very familiar. The LCD 16:2 module, and this one it's very also familiar. The 7 segment displays. Okay, and this is the programming modes switch, this small here, the programming mode switch. Okay, and this is here, this one here, the LEDs. These are the 18 red LEDs. Okay, and this one here is the 18 slide switches. Okay, and let's proceed with this one. The 64 MB SDR RAM, this two here. Okay, sorry for that. This two here. This is against the 64 MB SD RAM, and this one, guys, here is the 2 MB SRAM. Here, this one, guys. Okay, this one, and this one here is the 4 push button, okay? And this one here is the 8 MB flash, and here is the 8 green LEDs, okay? So here, okay, let's proceed here, this part here. So this is the IR receiver, this one IR receiver, and this one here, the SMA extension clock in, and this is the clock out, okay, of SMA extension clock out, okay? And this one here, this one here, this is the 50 megahertz oscillator, okay? 50 megahertz oscillator. And this one here, the big one, is the Altera 60 nanometer Cyclone 4E FPGA with 115K LES, okay? And this one here, this is the expansion, this one is the expansion header or J15 with protection diodes. And this one here is the HSMC connector again. This is the HSMC connector. And this one here, the center part here, this is the gigabit Ethernet PHY. And this one here is the PS2 port, okay? So, and this one here, last one, is this one here, it's the VGA 24-bit digital to analog converter, okay? This one. So those are the different components of the Altera DE2-115. So let's familiarize some of the specific components of the Altera DE2-115 by starting with the using of push buttons and switches. So the DE2-115 board provides 4 push button switches as shown in figure 4.6. Each of these switches is debounced using a Smith trigger circuit as indicated in figure 4.7. The 4 outputs called key 0, key 1, key 2, and key 3 of the Smith trigger devices are connected directly to the Cyclone 4E FPGA. Each push button switch provides a high logic level when it is not pressed and provide a low logic level when depressed. Since the push button switches are debounced, they are appropriate for using as clock or reset inputs in a circuit. So let's proceed with this one. There are also 18 slide switches on the DE2-115 board, see in figure 4.8. These switches are not debounced and are assumed for use as level-sensitive data inputs to a circuit. Each switch is connected directly to a pin on the Cyclone 4E FPGA. When the switch is in the down position, or which means closest to the edge of the board, it provides a low logic level to the FPGA, and when the switch is in the up position, it provides high logic level. So now let's proceed with using of LEDs. So there are 27 user controllable LEDs on the DE2-115 board. 18 red LEDs are situated about the 18 slide switches, and 8 green LEDs are found above the push button switches. The ninth green LED is in the middle of the 7 segment displays. Each LED is driven directly by a pin on the Cyclone 4E FPGA. Driving its associated pin to a high logic level turns the LED on, and driving the pin low turns it off. Figure 4.9 shows the connections between LEDs and Cyclone 4E FPGA. So here are the list of the pin names of the Cyclone 4E FPGA that are connected to the slide switches is given here in table 4-1. Similarly, the pins used to connect to the push button switches and LEDs are displayed in 4.2 and 4.3 respectively. Okay, so much for the using LEDs. Let's proceed with using the 7 segment displays. The DE2-115 board has 8 7 segment displays. These displays are arranged into 2 pairs and group of 4, behaving the intent of displaying numbers of various sizes. As indicated in the schematic in figure 4.10, the 7 segments common node are connected to the pins on the Cyclone 4E FPGA. Applying a low logic level to a segment will light it up, and applying a high logic level turns it off. Each segment in a display is identified by an index from 0 to 6. With the positions given in figure 4.10, table 4.4-4 shows the assignments of FPGA pins to the 7 segment displays. Okay, so that is about the using of 7 segment displays. Clock circuitry. The DE2-115 board includes one oscillator that produces 50 MHz clock signal. A clock buffer is used to distribute 50 MHz clock signal with low jitter to FPGA. The distributing clock signals are connected to the FPGA that are used for clocking the user logic. The board also includes two SMA connectors, which can be used to connect an external clock source to the board or to drive a clock signal out through the SMA connector. In addition, all these clock inputs are connected to the phase lock loops or the PLL clock input pins of the FPGA to allow users to use these clocks as a source clock for the PLL circuit. The clock distribution on the DE2-115 board is shown in figure 4.11. The associated pins assignment for clock inputs to FPGA I/O pins are listed in table 4-5 as shown. Okay, so this is about clock circuitry. So now let's proceed with the expansion header. The DE2-115 board provides a 40-pin expansion header. The header connects directly to 36 pins of the Cyclone 4E FPGA and also provides DC of plus 5V VCC5, a DC of plus 3.3 volts or the VCC3P3, and two ground pins. Figure 4-15 shows the I/O distribution of the GPIO connector. The maximum power consumption of the daughter card that connects to GPIO port is shown in table 4-10. Each pin on the expansion headers is connected to two diodes and a resistor that provides protection against high and low voltages. Figure DE2-115-4-16 shows the protection circuitry for one of the pin on the header, but this circuitry is included for all 36 data pins. The voltage level of the I/O pins on the expansion headers can be adjusted to 3.3 volts, 2.5 volts, 1.8 volts, or 1.5 volts using the JP6, or the default value is 3.3 volts as shown in figure 4-17. Because the expansion IOs are connected to bank 4 of the FPGA, and the VCC IO voltage, or the VCC IO4 of this bank is controlled by the header JP6. Users can use a jumper to select the input voltage of the VCC IO4 to 3.3 volts, 2.5 volts, 1.8 volts, and 1.5 volts to control the voltage level of the I/O pins. The table 4-11 lists the jumper settings of the JP6. The pin outs of the JP6 appear in figure 4-17 as shown. So note, users who want to use daughter card on GPIO connector need to pay close attention to the I/O standard between DE2-115 GPIO connector pins and the daughter card system. For example, if the I/O standard of GPIO pins on DE2-115 board is set to 1.8 volts, a daughter card with 3.3 I/O standard may not work properly on the DE2-115 board due to the I/O standard mismatch. Figure 4-18 depicts the pin definition on the expansion connector for using these I/Os as LVDS transmitters. Due to the reason that the column I/Os of the FPGA, the expansion pins connecting with can only support emulated LVDS transmitter to single-ended output buffers, and external resistors must be used as shown in figure 4-19. The associated I/O standard of these differential FPGA I/O pins on the Quartus project should be set to LVDS_E_3R. So the factory default setting on the RS resistor will be 47 ohm, and RP resistor will not be assembled for single-ended I/O standard application. For LVDS transmitter application, please assemble 120 and 170 ohm resistor on RS and RP position respectively. Finally, table shows all the pin assignment on the GPIO connector. Okay, so lastly, using VGA. The DE2-115 board includes a 15-pin D subconnector for VGA output. The VGA synchronization signals are provided directly from the Cyclone 4E FPGA, and the analog devices ADV7123 triple 10-bit high-speed video DAC. Only the higher bits, 8 bits, are used. It is used to produce the analog data signals, the red, green, and blue. It could support the SXGA standard 1280 by 1024 with a bandwidth of 100 MHz. Figure 4-21 gives the associated schematic. The timing specification for VGA synchronization and RGB red, green, and blue data can be found on the various educational websites. For example, search for the VGA signal timing. Figure 4-22 illustrates the basic timing requirements for each row horizontal that is displayed on a VGA monitor, and an active low pulse of specific duration time in the figure is applied to the horizontal synchronization input of the monitor, which signifies the end of one row of data and the start of the next. The data (RGB) output to the monitor must be off, driven to 0 volt for a time period called the back porch after the H-sync pulse occurs, which is followed by the display interval. During the display interval, the RGB data drives each pixel in turn across the row being displayed. Finally, there's a time period called the front porch, or D, in the figure, where the RGB signals must be again be off before the next H-sync pulse can occur. The timing on the vertical synchronization V-sync is similar as shown in figure -11-22, except that the V-sync pulse signifies the end of one frame and the start of the next, and the data refers to the set of rows in the frame horizontal timing. Table 4-14 and Table 4-15 show different resolution and durations of time periods A, B, C, and D for both horizontal and vertical timing. Detailed information for using ADV7123 video DAC is available in its datasheet, which can be found on the manufacturer's website or in the DE2-115 datasheets slash video dash DAC folder on the DE2-115 system disk. The pin assignments between the Cyclone 4E FPGA and the ADB7123 are listed in Table 4-16. An example of code that drives a VGA display is described in section point 2 and section point 3 in the manual. Note that the RGB data bus on the DE2-115 board is 8-bit instead of 10-bit on DE2 or the DE270 board. So that's it for the tools familiarization for the Altera DE2-115 and the Quartus.